Okay, so chapter 22, number 3, is the first up on our problems. So that problem says you measure an electric field of 1.25 times 10 to the 6th newtons per coulomb. So I'm just going to write that down because otherwise I'll forget. That would suck. Alright, at a distance of 0.15 meters from a point charge. 0.15 meters from a point charge. So we have our little point charge here. Bloop, bloop. And here's our little point of interest over there. Burp, burp, like so. There is no other source of electric field in the region other than this point charge. A, what is the electric flux through the surface of a sphere that has this charge at its center and that has a radius of 0.15 meters? And B, what is the magnitude of this charge? Okay, so in order to find the electric flux, that's the left side of our Gauss's law. That's our closed integral of E dot dA. This is not where an equal sign goes. Equals flux. Okay. So in this case, we have our little point charge over here. And we have our little point P over here. Boop, boop, boop. And if we draw a sphere, boop, 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 boop. I'd help if my lead was out. Boop, 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 boop. Boop, 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 boop. A distance r away. That is the Gaussian surface that we're going to look at. Yeah, that's in the middle. I can't draw. Sorry. Alright, so in this case, because this is a point charge, our electric field is coming radially outward, right? So at this point that we care about, it's coming out tangential to that, not tangential, what's the word? That's not tangential. Normal. It's coming out normal to this spherical surface right here. So that's my E field. My dA vector also always comes out normal to the surface. So there it's that way, here it points this way. So for a sphere, our dA vector also comes radially outward. So at this particular point, E and dA are parallel to each other. So when two things are parallel, vector dot vector, their dot product just turns into the multiplication of their magnitudes. That's the way that works. Alright, so other things that we can say about this, because this is a sphere, it has a nice happy radius. The electric field at that same radius all the way around is going to be constant. And that's going to generally be the case with Gauss's law because it's not useful to use it otherwise. So our electric field is constant all the way around, so we can pull it out of our integral. So we just get the integral of E, or the integral of dA. And the integral of dA all by its lonesome is just A. E times A. So in this case, the A is that of a sphere, which is 4 pi r squared. So if we stuff in some numbers, our flux is given by the electric field 1.25 times 10 to the 6th newtons per coulomb times 4 pi r is 0.15 meters to the squared. So if we punch that into our handy dandy calculator, which I'll do later. Actually, I'll do it right now. Okay, so we're going to punch that into our handy dandy calculator. Do. 1.25 times 10 to the 6 times 4 times pi times 0.15 to the squared gives us a flux of 353.429 Newton meters squared per coulomb. or if you like scientific notation, which you should because it's way better than literally everything, 3.5 times 10 to the 1, 2, 3, 4, 5 Newton meter squared per coulomb. Ta-da! Okay, so for part B, they want to know what the magnitude of that charge is. So then we're just going to use the other half of Gauss's law. So our closed integral of E dot dA is equal to Q enclosed over epsilon naught. We already did this side. We have a number. Sweet. So we can solve for Q enclosed. So the charge enclosed by this handy dandy sphere is just our flux. I'm gonna write that up here. Equals flux. Flux times epsilon 0, or 3.5 times 10 to the 5 newtons meter squared per coulomb, times epsilon 0, which is 8.85 times 10 to the minus 12, and I can't remember the units, so I'll type that in a second, times 8.85 times 10 to the minus 12, because splat, units is equal to 3.13 times 10 to the minus 6 coulombs, or 3.13 micro coulombs, splat. Bloop, bloop. Alrighty. And that's it. The end. Woo!